All right. So hello, everyone. Welcome to Mechanical Engineering Seminar Series. Today, it's our pleasure to have Abhishek Halder from the Department of Applied Mathematics at the University of California, Santa Cruz. So it's a great pleasure to have him here. But just a brief introduction to his bio. Abhishek is, as I mentioned, is currently an assistant professor in the Department of Applied Mathematics, and he's also an affiliate faculty in the Department of Electrical and Computer Engineering at University of California, Santa Cruz. Before joining UC Santa Cruz, he did 2 postdocs, one at the University of California, Irvine, in the Department of Mechanical and Aerospace Engineering, working with Trifon Giorgio, and the other one at Texas A&M University in the Department of Electrical and Computer Engineering, working with P.R. Kumar. He did his Ph.D. In the aerospace engineering at Texas A&M University, where he received the Outstanding Doctoral Student Award. And he did his bachelor and master's in aerospace engineering at IIT Kharagpur, where he received another award for best dual degree thesis. His research interests are in stochastic systems, control and optimization, with application focus on large-scale cyber-physical systems. He's a co-founder of the annual NorCal Control Workshop that brings together systems control researchers from academia and industry in the Northern California region, fostering collaboration and professional networking. Without further ado, I'll give the virtual floor to Abhishek to share with us what he has to say.
Thank you, Ali. Thanks for the very generous introduction. Thank you all, and hi, Peter. Nice to meet you.
Hi, we had some trouble getting online here, so I hope that
that was my bad. The link didn't have the dash, so the link was failing.
It's been
so thanks for coming.
We're very much looking forward to the talk. We're very happy we've just managed to climb in.
Thank you. Thank you so much. Thank you so much for making time to attend this talk, and thank you all for attending. And I'm very happy to meet you all virtually, and I hope that sometime soon I can visit. And thanks again for giving me this opportunity. So what I'm going to present today, this is a very recent and perhaps a little bit preliminary at this stage, but still I decided to present this work because perhaps some of the ideas could be interesting. This is a joint work with 2 of my graduate students, Iman Nodozi and Alexis Tater. Iman Nodozi is a Ph.D. student at UC Santa Cruz in the Department of Electrical and Computer Engineering, and Alexis is a Ph.D. student in the Department of Applied Mathematics. Okay. All right. Okay. So the thing that I'm going to discuss in this talk is the main topic concerns with optimization over the space of measures or distributions. And because of the nature of this, the topic, there are some technicalities in this topic. So what I decided to do is keep things at a very intuitive level. Okay, so I may be glossing over many of the technical issues, but perhaps those are intentional. So if you would like to interrupt me, please feel free to do so. Okay. But I will keep things at the intuitive level. My main intent is to get the main idea across of what is the overall broad picture view and what are the ideas that we are pursuing. Okay. All right. So what do we mean by measure or distribution? So let's start from the very basic. And those of you, who are perhaps in the mechanical engineering and not, really in the controls area, but perhaps have worked in the fluids area or the materials, you already know that basically in terms of materials or fluids, the measure or distribution refers to essentially mass. Okay, so this is a pretty much good way to think about these things. And you also know that mass is essentially equal to density times volume. Okay, so we will be appealing to basically the same intuition. The only thing we are going to do here is the same idea carries over to more abstract settings or more mathematical settings, where that we may be talking about not material mass, but maybe probability mass or probability measure or probability distribution. And there also the same thing will happen, that is equal to some density function. In that case, it will be probability density function times some volume. Okay. Similarly, we may be talking about some population mass or population measure or population distribution, that will be equal to some population density function times some volume. Okay. So the main takeaway from here is the words measure and distributions are synonymous, and you can roughly think about them as mass, okay, without any loss of generality. Okay. So here is a very basic cartoon to motivate the ideas. Suppose we want to talk about probability distribution in a dynamical system context. So suppose I want to talk about the state of a mobile robot in a plane, in a two-dimensional plane. So this can be described as the state vector x. This x is a 3×1 vector. Okay. So already there is a typo. So it should be equal to x, y, theta. So basically this 3×1 vector xt is a 3-tuple. So the first two numbers, x and y, refer to the horizontal and vertical position coordinates, for example, in feet with respect to some coordinate system. And the third entry theta, which is a radian, which basically measures the orientation or the heading angle. Okay. So if there is no uncertainty or nothing probabilistic about it, then if somebody asks what is the state of the robot, we may as well return at time t this specific 3×1 vector, or this 3-tuple, 2 positions and 1 heading. Okay. But when we have some uncertainties in the state, then we may want to say what is a distribution of the state over this 3×1 state coordinates. Okay, so that is usually given by what is called this rho or probability density function. This is a joint PDF or joint probability density function, which is a function of the state x, comma t. Okay. And what it does, it is a function that is integrates to 1, which basically means that probability at all times, probability mass is conserved. So we write like this: integral over d mu is equal to rho times dx. So this is nothing but this previous page, mass equal to density times volume. Okay. So here mass or the probability measure is this mu, and then density is a function, which is a probability density function, giving which are the high probability regions in the state space and which are the low probability regions. So this is at every time, this is supported over a 3-dimensional state space. Okay. But its shape may be changing with time, but at every time it integrates to 1. Okay. So rho is this probability density function and dx is the volume here. Okay. So d vector x here means d small x times dy times d theta. Okay. Okay, that's about probability. We can think of this as an alternative way, which has nothing to do with probability, which basically refers to the fact that distribution may also be over populations. Okay, so on the right panel, what you are looking here is, suppose you have a collection of robots, suppose you have thousands of them, and they are spatially dispersed. Okay, they are spatially distributed. So you, roughly speaking, thinking like swarm of robots in the 2-dimensional plane. Now, some of them are have concentration, spatial concentration, which is very high in some regions of the space. Some of them have low concentration in other regions of the space. And you may ask the question, what is the population distribution? Okay, so there the population measure is essentially measuring the number distribution. Okay, for example, in this right figure, it is showing that the most of the robots are oriented to the right. Okay. So for our purpose, it will not matter which interpretation is in play. That really is governed by the application, but the math we are going to talk about will go through in both these cases. Okay, so I'll not make a distinction from this point on. What do we mean by measure or distribution? Are we talking about probability or populations? The math goes through, the same math goes through. The one other background concept that I will need to talk about geometry on the space of probability measures. Okay, so now I have already started talking about measures in the sense of probability, but again, as I said, this interpretation remains valid even if we want to talk about population measures. So imagine a space where every point defines a probability measure. Okay, so this is a space of functions, and suppose I'm given two different measures, this mu0 and mu1. Okay, then what I want to do, I want to describe the geometry of this space. And the first thing that we do in geometry, we somehow want to define a distance metric on this set or on this space. Okay, that distance metric, if we can define it, and if this notion of distance indeed turns out to be a metric, then we can talk about things like what is the shortest distance, and we can even start doing some calculus on this space. So one popular way that has been inspired by many recent advances in optimal mass, what is called optimal mass transport theory, and that has gained traction across many areas in control, physics, machine learning, and mathematics in recent years. So one popular way to do this there is to define what is called the two Wasserstein distance metric. And the definition that I'm showing here, this is what is called dynamic or Lagrangian definition of this distance metric. What it is doing, if you look at the right-hand side, it is defining the distance metric or distance between two given measures or distribution mu0 and mu1 as the solution or minimum value of an optimization problem. Okay. Now let's look at what is this optimization problem. It is asking to minimize something. And if you pay attention to the objective function, what it is trying to minimize, so there are two integrals going on, and in the inner, the integrand has some v square d mu. You already know that d mu is basically differential of mass, and v is some velocity vector field. Okay, so this is an optimization over a pair mu comma v. Okay, so if d mu is some mass times velocity square, this is roughly speaking, again, I'm appealing to intuition, not to rigorous mathematics, d mu times v square, roughly speaking, is mass times velocity square, is kinetic energy. Okay, and that you integrate over x, which is your spatial variable. So this is the total kinetic energy while holding the time fixed at a fixed time. Okay, and then you integrate over 0 to 1, which is the time. Okay, so this is kinetic energy times time. This is total work done. Okay, so it is trying to minimize the total work done in moving this distribution, starting from this distribution mu0, that is the initial condition, mu at t0 is some mu0, and mu at t1 is mu1, it is some terminal condition. And then there is additional constraint, which is essentially, if you think like fluid dynamics, this is essentially the continuity equation or Euler equation. So it is saying construct a velocity field, okay, under which you move the probability measure starting from this given distribution mu0, and you want to end up to this given terminal distribution mu1. So mathematically speaking, this mu, this is optimization is over a pair of variable mu and v, but what is really happening here, this optimization is happening over the path space, or path space measures mu. Okay, in other words, it's basically going to give you a measure value trajectory. Okay, so this is this trajectory, this line is connecting this mu0 and mu1. Now, of course, you can connect many lines, right? So what is asking, what is this optimal line, in terms of optimal in the sense of that minimizes the total work done. Okay, answer of this optimization problem is going to give you W. Okay, this W subscript 2 is given. Sometimes I'll be dropping 2 because it's too much mess already, notationally speaking. So to reduce clutter, sometimes I'm going to drop this 2. So we'll always going to refer to this W2 as a 2 Wasserstein or a Wasserstein metric. Okay. All right. Now, the nice thing about this metric, distance notion is that it is genuinely a metric, meaning it satisfies all properties of being a metric. And it in fact induces what is called something like a Riemannian-like geometry on this space, meaning you can actually start doing calculus. You can in fact define the path that is connecting, generated by solving this problem, that is actually a measure value, what is called geodesic. So think of it as like a shortest path connecting this given mu0 to given mu1. Okay, and that can actually also be solved like this way, which is closer to this, finite dimensional geometry definition of geodesic, which is basically, now this time it's a static problem. You are minimizing and you want to find the argmin or the minimizer over the space of, or the manifold of all probability measures supported on some base space X, which could be some Euclidean space with some finite second moments. Okay, and that, yeah, questions?
So very quick question, does the minimizing path always exist? I mean, what are the conditions where the infimum doesn't turn into a minimum?
Yeah, so the good thing is that this exists in, existence, uniqueness are guaranteed and, very, it's very mild assumption. So for example, if, we should go back, if mu0 and mu1, the initial and terminal, if they have finite second moments, then it is guaranteed that, this will exist, okay? And it is unique. So that means that they don't even need to have, need to be compactly supported. I mean, even not absolutely continuous, okay?
Thanks. And Shuang is asking, would WP metric have a similar nice representation?
Yes, that's a very good question. Is WP, if W instead of 2, if you have P, there is a similar result is possible. There are some technicalities. For example, if P equal to 1 and infinity, those cases are a little tricky. But what happens is that, for roughly speaking, for different P, the thing that you change, this V square, that is basically 2 norm square, okay? So that, that functional gets changed, okay, to, some other functional that depends on this P, okay? In general, you can actually even define mixed norms. For example, WPQ, where this power 2, this would be P, and this would be Q. So this half is, roughly speaking, inherited by this distance, whereas this 2 is inherited by the base space. So this V square is coming from the fact that, this X, which is the ground space or finite dimensional space, their distance is measured via straight line, okay? So if the ground space has a different notion of distance, so that will show up here. For example, if the ground state has, something like, V transpose G inverse, some Riemannian metric, so that will come up here. So this is, roughly speaking, the ground cost, okay, this V square.
I have also a question. So why do you need the mu and the m? Because it's uniquely determined by V, right?
You don't need it. So what I'm showing here is that there is a connection between these two. The first one is perhaps some little bit abstract way to define the it's scalar, and whereas here this is little more like a static optimization way of defining the individual points. So think about the bottom part as a static optimization problem, which for a given t, so you choose, let's say t is 0.7. So it is going to enumerate point by point, on this curve.
No, I meant in the env and the W2. So env over mu and V. And mu is a function of V, right? It's uniquely determined by V.
No. Mu is not a function of V. Mu and V, these are, it's a joint optimization over the two variables, mu and V.
Oh, okay. Because I thought from the constraint, you'll get mu as a function of V, right? As a unique solution of this differential equation.
Mu is, think of this as a, suppose I give you V, right?
Yeah.
Then that determines mu, right?
Yeah.
V is not given, okay? So what is happening here is that you need to jointly determine mu and V. So it's a joint.
I see, yeah.
Optimization over mu and V.
Yeah.
Sure. Those of you who know some control, this has a very simple control interpretation. So instead of thinking this macroscopic dynamics, partial mu, partial t is, this minus of this divergence of mu v, you can think the corresponding, the particles are flowing according to it's a simple single integrator, x dot equal to v, okay? So basically v need to be designed, okay? So v determines how the individual particle, their flows will look like. In general, v is a function of x comma t, okay? Okay, so that's background. All right. So now the type of problems we're interested in is, we would like to solve some optimization problems of the following form. We would like to minimize some functional of this, measure mu, which could be a probability measure or a population measure, depending on application. And the optimization happens over this space of mu, which belongs to this P2 or some probability measures, which are supported, instead of X. Now, this time I'm writing more simply, just let's say RD, some D-dimensional Euclidean space, okay? And this F is convex in the sense of this 2 Wasserstein metric, okay? So, because now we are talking about functional optimization problems, so we need to be careful what do we mean by convex. So it is convex with respect to this distance. And in many applications that I'm going to talk about, not only we want to solve this problem, there is additional structure that F has this kind of additive decomposition. It is a sum of some other functionals, and each of them are also nice in the sense of these are proper, it's what is called lower semi-continuous, and they are also this convex in the sense of this 2 Wasserstein geodesics. Okay. Now, what kind of situations require this kind of problems? There is a very intimate connections with these problems with what is known as Wasserstein gradient flows. The fact that we have defined a geometry using this metric, that allows us to actually define or essentially do calculus over the space of measures, okay? So what you can do, you can define partial differential equations of the form partial mu partial t is negative of the gradient of this functional f of mu with respect to this distance W2, and this is defined like this way. You take the Frechet derivative and then take the Euclidean gradient grad and then hit it with mu and then take the divergence of this, okay? And this kind of equations have the interpretations that, if we can write, suppose we have encounter some practical partial differential equation in some applications, and suppose we can come up with this functional, suppose we reverse engineer this functional f of mu, and then we interpret solving that, let's say, initial value problem involving that partial differential equation has this nice interpretation of this is the gradient flow of that functional f of mu that I just reverse engineered with respect to this metric W2. Okay, so this is a gradient descent of this functional f with respect to this particular metric, okay, on that space P2. Now, why are people interested in this kind of things? There are two types of motivation here. One type of motivation comes from the fact that in some applications, people really want to solve the stationary solution of some PDE, okay? And then by leveraging this connection, they will say that, okay, if this interpretation holds, then the stationary solution of the PDE may be viewed as a minimizer of this optimization problem, okay, which is basically the optimization over the space of mu, because f is this convex with respect to this W2 sense. The other type of application is that people are still interested in the PDE, but they are not interested in the stationary solution. They are actually interested in computing the transient solution, meaning not t going to infinity, but actually at some intermediate t, maybe small time solution. Okay, so even then, this is useful in the sense they may say that instead of solving a PDE like a PDE and appealing to traditional scientific computing like finite volume, finite difference, we may be attacking a PDE solution problem via optimization perspective. So instead of solving a PDE as a PDE, we may be solving it as a discrete time stepping, realizing some gradient descent of this thing. Okay, so what do I mean by that? There are certain type of numerical schemes which go by the name of Jordan, Kindle, Lehrer, Otto, JKO scheme. This is introduced in 1998, has become very famous since then. And they essentially exploit the idea that, in finite dimensional, there is a gradient descent may be viewed as recursive evaluation of some, Euclidean proximal operator. I'm going to define what that means. But the same idea, once we have made a connection with gradient flow or gradient descent, the same idea can be, also carried over to this setting, of optimization over the space of measures, which is on its face is an infinite dimensional optimization problem. Okay, so what do we mean by these gradient flows? On the left panel is something that all of you know. On the right panel is something that I'm talking about. On the left panel, if you talk about gradient flow in some finite dimensional space, then what you have is an ordinary differential equation, and you have x as a function of t, which is negative of gradient of some suitable function, some initial condition. That you may implement essentially like a backward Euler discretization, right? X next is equal to x previous minus some time step h times gradient of that function. But that may be exactly rewritten as this, this static optimization problem, which is arg mean over x, small x, half of Euclidean distance square between x and the previous iterate x, k minus 1 square, plus h, which is time step times this function that you are trying to minimize. Okay, so there is no approximation here. It is simply, a completion of square and some rewriting and throwing away stuff that does not depend on x. This kind of optimization problem, which has this structure half into some distance square between the previous iterate and my optimization variable plus time step times the function that I'm trying to minimize. This kind of optimization problems are called proximal operator, which is this notation, prox of h times f, is time step times f, which is this thing, second summand. And this superscript 2 norm is basically saying it's the proximal operator with respect to Euclidean distance of the function h times f acting on the previous iterate xk minus 1. So that is going to give xk. Okay, so the way you think about it, you think of this as a recursive machine, input output machine. You feed in xk minus 1, comes out xk. Again, you feed that, output becomes input, and the next time step goes in. Now, as you keep on evaluating this machine, what it does, it generates a sequence of vectors. As the time step h goes to 0, this sequence of vector converges to the solution or trajectory generated by this solution of this ordinary differential equation. And there is some connection with Lyapunov function. I'm not going to emphasize that. Approximately speaking, the same thing happens on the right-hand side. Instead of a ODE, now what you have is a partial differential equation. Partial mu, partial t is negative Wasserstein gradient of some functional. And you can also write down a recursion. The recursion is not in algebraic form. So mu next is, but can be written in the proximal form. It is the arg mean over probability measures in this P2x half into some distance square, in this case W square, between the optimization variable mu, comma the previous one, mu k minus 1, plus h times or time step times the functional that I'm trying to minimize. In this sense, it is a proximal operator of the functional h times f with respect to W. Okay, just like gradient descent, in the Euclidean gradient descent can be seen as a proximal recursion with respect to Euclidean metric of the scaled functional that we're trying to minimize. In same way, Wasserstein gradient flow can be seen as the gradient descent of the time step times the functional that we're trying to minimize with respect to the W. Okay. If similar convergence guarantee, if you run this, it is going to generate a sequence of measures that converges to mu, which is the solution of the PD as time step h goes to 0. Now there is some technicality here because what do we mean by convergence of measures? So in general, this guarantee is actually very strong. It is what is called strong L1 convergence. Okay. Again, the Lyapunov functional interpretation goes through, but I'm going to ignore that. What are the motivating applications for this kind of problems? One motivation, and this is appealing to the static interpretation. Suppose you want to only compute the stationary solution. That kind of situation happens in statistics and machine learning in the problem of simply sampling from a complicated distribution. So the idea is that you think about, you have a complicated unnormalized prior. To sample from that prior, what you do, you engineer essentially a stochastic differential equation whose stationary solution is basically the desired measure. Okay. Then the idea is to run this kind of algorithms for multiple samples for a long time, and it is going to converge to the distribution where we want to sample from. Okay, this kind of algorithms goes by the name of Langevin sampling, and there are many variants and a lot of work on this. This is, by no means a new idea. There is a very, very significant literature. Many different communities have worked on this. The connection with our work is that this can be viewed as the solution. If you write down the generator corresponding to those Langevin stochastic differential equations, you again get a Wasserstein type of gradient flow of some suitable functional f. Okay, there is similar connection with what is called optimal control of distributions, or these are called Schrödinger bridge problem, and something that very exciting work is going on in control community, including very exciting contributions from Ali. So there, the idea is you want to design feedback control that steers a given distribution or density function, let's say rho 0, to another distribution rho 1, which is this gray one. If you do not do feedback control, that is not what happens. And this is a problem to be solved over finite horizon. And you want to minimize some control cost, which is in the sense of, the traditionally, let's say quadratic cost. So the only new thing that is happening here is the boundary conditions are not on the space of, finite dimensions. Instead of going from one point to another point, you want to go from one distribution to another distribution. So you can think of this as a statistical specification of control performance. Okay. There is a third line of application, which is somewhat recent. There are a bunch of papers, like actually 3 different groups simultaneously came up this idea in 2018. The idea was that to think about the mean field learning dynamics in neural networks as Wasserstein gradient flow. Okay, so the idea here is that you consider a neural network which is very wide, okay, and you think of this as a infinite width limit, okay. But otherwise, you think the the network is shallow. It's not a deep neural network. It's a shallow neural network, meaning it has only one layer, but it is over parameterized, meaning you let the number of hidden layer neuron go to infinity. In that limit, you can think there will be a lot of these neuronal units, and this will become a continuum population. Then you can think about a population measure over the space of these parameters, okay, which are basically to be trained as a neural network training procedure, okay. Then you can say that, instead of optimizing over theta, which is known to be a finite but large finite and non-convex optimization problem, I may only want to optimize over the population measure of theta, okay. And surprisingly, it was shown that in all these 3 papers that this problem can be rewritten as a Wasserstein gradient flow, meaning in the mean field limit, there is a PDE induced by the stochastic gradient descent learning dynamics, okay, and that has exactly this structure, this kind of structure, and therefore it can be seen as a gradient descent with respect to some functional. Okay, there are also connections with much traditional problems in control and dynamical systems. For example, if you want to view uncertainty prediction or nonlinear filtering problems, there are some works which show that these problems may also be viewed. In unsafe propagation, you have a just prior distribution, and in nonlinear filtering problem, you are interested in the flow of the conditional joint distribution. Even those problems may be viewed as some kind of gradient flows. There is a question in the chat. There is a question, does one respect the graph structure in this setting of mean field in neural network? In this setting, we are assuming that this is all-to-all connection topology. Okay, so that's where the existing results are known. Yes, all-to-all connection topology, single hidden layer. Okay, so and so it's a shallow neural network, but you let the number of mean field basically means you let the number of hidden neuron go to infinity. So it's an infinite width limit. Okay. All right. Okay. Now, this is not only just theory. Recently there has been an explosion of interest in this, just numerically implementing these such algorithms. So, and the only thing I want to say here is that I don't want to go through the list of these papers, but perhaps the only thing to say is these papers are coming from many different communities. So there are people from imaging sciences, there are people from traditional math analysis, then there is a control, and then computational mathematics and more mainstream machine learning conferences. And they are motivated by different applications, but they are ending up with the same computational problem, how to compute this kind of Wasserstein gradient descent or flow in the numerical level. But all of this requires centralized computing. Okay, and now what is bad about centralized computing? For moderately sized problem, there is no issue, but when you go into machine learning type of problems, so here is one problem we recently investigated, and it's basically has to do this with, with the mean field, the stochastic gradient descent dynamics that I talked about. And we considered the very simple situation, which is neural network classification. And in that case, what happens, this f mu, this functional of the measure takes this form. This is some risk of this f hat. This is the neural network approximation that you are trying to learn, which now is a function of this mu, okay? That as a result, this left-hand side is a function of mu. And if you take this risk as a quadratic loss, which is standard, and then you can expand it out, some a minus b whole square essentially, and then rewrite it as this kind of functional, which is a sum of something f0 that does not depend on mu, and then there is a term which depends linearly on mu, and then there is a term which depends non-linearly on mu. Okay, so this last term is like a generalized convolution. Okay. And this VU, these are, in dynamical system sense, these can be thought of as V can be thought of what is called advection, and U can be thought of what is called interaction potential. But these, in the neural network context, these are essentially functions of the activation functions that are using in the neural network architecture. Okay, so they depend on the activation function. Again, the same story. There is a partial mu, partial t, which is negative of Wasserstein gradient of this particular function in this setting. And the idea that we pursue to implement it essentially as this proximal recursion using some prior work that we did. And all of this is centralized. Okay, there is nothing decentralized or distributed computation. And we basically got reasonable results. So the risk functional decays after 1 million iteration, but this is quite a significant computation. Okay, and this is a not a heavy this is not something that is considered a challenging benchmark. This is a very standard benchmark. The idea is that you are just trying to do binary classification, and but the computation is new. In the sense, what we did, we are essentially, instead of just doing stochastic gradient descent, we also implemented this proximal recursion. So we are essentially evolving a joint PDF over, in this case, 32-dimensional parameter space. Okay, and if you run this in CPU, it takes approximately 33 hours of runtime, and we did some GPU implementation with essentially spending 1 year behind this by doing all kinds of parallelizations and meshless implementation, everything we could think of, and even after that, it came down to 2 hours of runtime. The results are, accuracy is not bad, but it's comparable to the existing state of the art, but its runtime is significant. So the question that we really wanted to pursue, I am almost towards the end of the time, but the question that we wanted to pursue here, so the main research question is, do we really have to do it like a centralized computation? Can we not take advantage of the fact that the objective is not just some f of mu, but that in all practical applications usually have this additive structure. So how to take advantage or leverage this additive structure, although this is not separable, but at least additive, and to leverage that to design distributed algorithms, okay, to solve this kind of optimization problems. So the idea is very simple, and those of you who are familiar with this finite dimensional optimization, what is called ADMM or alternating direction method of multipliers, we essentially follow the same footsteps. The idea is that because it is not separable, you forcefully write it in a separable form, and then you artificially impose this constraint that all of this mu1, mu2, up to dot, 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 up to mu n, they are essentially the same thing, which is equal to this something called this zeta. Okay, essentially what is happening here, you increase the dimensionality of the problem. Original problem is over single measure. Now you are saying that you have to optimize over n+1 measures. Okay. Why would anyone do that? Well, if you do that, then just like the standard Euclidean ADMM, you define what is called Wasserstein augmented Lagrangian, which has this sum structure, which is this basically sum of these individual functionals, plus there is a regularization term, which in the Euclidean case would have been Euclidean distance square between this mu I, okay, individual measures, and zeta, which will go to 0 if there is this constraint is imposed, right? And then you have this Lagrange multipliers, which are basically corresponding to this equality constraints. Okay, this Lagrange multipliers are now the functions. Okay, and then you implement exactly what you do. this is a consensus ADMM problem. The reason it is called consensus is because you want all of these mu1s to be equal to zeta. So if you have arrived at the solution that this condition should hold, which means that this term, middle term, should go to 0. Okay, so we write it in this form, just like how it is done in Euclidean ADMM. So the first line is minimization over mu y, okay, which is now separable, and the second line is not separable still. It's a centralized computation problem. Zeta k plus 1 has to be minimization over zeta of this Lagrangian, and the last line is very simple. It's basically a dual ascent. It's just addition and subtraction. Okay, so the real challenge is how to do the first two lines. If you do some computation, you can show that this can be rewritten in the following form at the bottom of this page. This mu I k plus 1 is exactly the proximal operator of the functional 1 by alpha, which is some scaling, times this fi, okay, plus some integral of this nu I, which is some this Lagrange multiplier, acting on this zeta, and then there is a second line, the zeta k plus 1. This line takes this form, which looks a little bit interesting, and the third line we do nothing. Okay. Now the merit of this is that if we look at the first line, what has happened, the energy or the functional has been split. The left hand side variable has an index I, so you can think about this as a computer index. Okay, meaning this problem may be solved as ith computer, okay, which will only need to solve a sub problem which has to involve only fi, okay, which is part of the function, only ith summand. Okay, so in other words, if I have n functionals, if I have n computers, everybody is solving a different problem, not the same problem. Okay, and this is essentially the idea of operator splitting, which is also well known in the literature. So we are essentially doing operator splitting over the space of measures. Okay, so this is the split free energy functions, but there is this extra term which is like a coordinator. Okay, this is the dual variable. And therefore, this first line is same as doing time updates of some partial differential equations or Wasserstein gradient flow of some the split functional. Here I listed some names. If f has some particular forms which are encountered in literature, I mean in particular applications, then you get into some particular partial differential equations. Okay. So let's see how to use this. So what we do, we directly write down the discrete version of this proposed ADMM over the space of measures. And if you write down directly discrete, then you get something like this. This nested minimization is appearing because W is not analytically known. It's answer of a minimization problem. Then the standard approach is to regularize the inner minimization by doing what is called Sinkhorn divergence, which is basically an entropy regularization. You add an extra term, epsilon log m, which makes it strictly convex, and then the recursion takes this form. And this has a very interesting structure. So this is outer layer ADMM. This is already how it is proposed, but the inner layer, which seems to be a centralized computation, also can be done via distributed computation. This is what we call inner layer ADMM. So what is appearing here is a two-layer ADMM. Now, if you remember what happens in Euclidean case, this second line essentially becomes arithmetic mean. It's actually analytically computable. Okay, so in Euclidean case, the first line is called x update, second line is called z update, and third line is this Lagrange multiplier update or dual ascent. So the x update has become proximal, and the z update or zeta update here, it has something to do with mean, but it is not the arithmetic mean. In fact, it's not even analytical. It is like what is called a Wasserstein barycenter with an extra linear regularization. Okay, so it's a mean in the Wasserstein space with the extra linear function. So let me just give the basic idea how the computation looks. The architecture looks like this. Suppose you have a central processor and you have some distributed processor, and suppose we have n is 3. I have only f is equal to f1 plus f2 plus f3. Okay, 3 split. So what is happening in distributed processor? There is this outer layer ADMM that is solving this mu update. Okay, so mu1, mu2, they're solving different problems. Different computers solve different problems. And once they solve it, they pass it to downstairs distributed processor. We call it this inner layer ADMM. What that does, that gets this information and unicasts that to inner ADMM minimizer. I'm going to talk about what this is, to some central processor. And from central processor, it gets back this zeta. Okay. Now, each of them also is sending this mu. Okay, so this mu and this information is used to compute zeta, and that is being sent back. Central processor is broadcasting that information to all the distributed computing elements. And this goes on, and this recursion repeats over iteration index k. Okay, that's the main idea. The outer layer, this mu update, depends on what kind of f we have. If this thing is linear, meaning like you only have drift, that happens in practice, and then in fact there is no recursion, it's actually analytical. If you have something like convex, very general setting, plus you have this extra term, then also it can be done by some recursive update, which is guaranteed to converge. The zeta update, this inner Euclidean, is more interesting. This is something new. This does not appear in the Euclidean finite dimensional case. There we get arithmetic mean, but here we have to solve this problem, and this still looks like a centralized problem, single optimization over zeta. There is no index I here, but surprisingly, the structure that is appearing here can be taken advantage of, and we can even distribute that computation. The result here is this. Suppose you consider the following finite dimensional convex optimization problem, which is over U. Okay, and it has this budget constraint or allocation constraint. Suppose you solve this U. These solution of this optimal U's, once they are solved, will give you zeta, okay, analytically. So only thing to be solved is this thing numerically. All right. So this is what is going on in this lower line of unicast. So this is, they are sending out the U update. Okay. Now, even this problem has some structure. Even this has a summation or the separable form. And here BY is unknown. These are solved from upstairs ADMM. Okay. So only thing unknown is UI. So that this looks like weighted log sum X type of problem with some equality constraint. And this one we can implement by what is called this Euclidean ADMM standard. This is finite dimensional ADMM. Only thing new here is that this last line, this proximal, there is another proximal update appearing, but this is not analytically computable, but can be done very quickly by Newton's method, like 5 iterations or so. Okay, so here is some results. So I'm going to show 2 very preliminary results. One is this experiment 1. This is the simplest example possible. We just take linear Fokker-Planck-Kolmogorov partial differential equation. This is the PDE we'd like to solve. And this has some drift is some gradient of some potential, and there is some linear diffusion. Okay, and this potential has this nonlinear structure, and it is known that this analytical solution of the transient solution is not known analytically, but the stationary solution is exponential of negative of some scaling times this V, which looks like this bimodal distribution. In our earlier work, we actually computed this by the centralized computation. We also proposed an algorithm that gets the solution. But the new thing we are doing here, this time we are doing it via this consensus algorithm. So we say that, okay, there are 2 terms on the right-hand side. What if each computer solves, individual terms? Okay, so one computer solves only a PDE, which has this F1 mu, and it solves that corresponding proximal optimization problem. The other computer solves, optimization problem that only involves this diffusion term. Okay, this log mu and mu. Okay. And if there is consensus, if everything is working, they should go to the same solution, right? So that is what you visually see is happening over 5,000 iteration. It is, getting to this, their results are matching because there is this data exchange in the ADMM algorithm via this Lagrange multipliers. We used, the worst computer we could find, MacBook Air 1.1 gigahertz. This took 90 100 seconds approximately, so it's very fast. Okay, and the solution matches with the centralized computation. A slightly more challenging problem, this is the last example, is this the similar type of partial differential equation, but this time we have aggregation also, meaning we have this nonlinear interaction term. Okay, so there is this convolution operator, and so there are 2 potential. One is drift, another is the diffusion. This is an example from the literature. It's a well-known example. So both are nonlinear, both are singular potentials, and even the diffusion term is nonlinear, right? So this is Laplacian of mu square. Okay. So what is known here in the literature, if you the stationary solution of this partial differential equation, in the limit this beta inverse goes to 0, this goes to a uniform distribution over some annulus whose radius, inner and outer radius, is known. Okay, and here what we did is that we said that, all right, there are 3 terms now. Now we have got choice. Unlike earlier problem, we have 2 terms, you can only do 1 plus 1 splitting, right? Here you can do either 1 plus 2 splitting and 2 plus 1, etc., etc. So one way to split it is just, take the interaction term as one splitting and the drift and diffusion as another splitting. And, we know that how to do proximal updates for each of these. And then again, do the similar simulation. Again, they are, matching, not only matching, even quantitatively, we can measure the radius, inner and outer radius. So we can get this half and square root of 5 by 2. And if they're really matching, so we should also be quantify the distance between the mu1k answer of the first computer solution and answer of the second computer solutions as they're evolving. It should go to 0 in the Wasserstein metric. And that is what you see is going on. Okay. We did the experiment also with, multi-way splitting, because, there is no reason we have to just stick with, take that particular combination, drift and diffusion together and interaction separately. Why not do the other way around? So we did all possible combinations, and in all possible cases, it converges. And each cases, because there is this randomness, so we did 100-run statistics. It's a very narrow band. Essentially, it converges. Okay. Runtimes are not bad at all. So the average runtime is, it's less than 5 seconds. Okay. All right. So that's all I have. Here's the summary. I think I'll leave time for questions, but I took almost all the time. But I hope there is some time for questions. What we are working on now is convergence guarantees. We do have convergence results that the whole thing converges as a consistency guarantee. What we do not have yet is the rate of convergence. That seems a little more challenging. And we are also working on high dimensional case studies. So I'll stop there.
All right, thank you very much. Let's join me in thanking Abhishek for the wonderful talk. And if you have questions, the floor is open for questions. Peter?
Abhishek, fascinating talk. I believe you've done some applications in recursive estimation, linear and nonlinear filtering. Would you like to make some remarks about that?
Yeah, that's a very nice question, and thanks for asking that, Peter. So let me see if I can go back. I did not actually mention anything about that in this talk. So we did some work here. So this, the work you are referring to are here. In the filtering, this is a fascinating question, and we, to be honest, we did not never have attacked, have not yet attacked the problem in full generality. So we have this 3 papers with Trifon, CDC and SSC. And what these papers show is that if you have linear Gaussian cases, meaning think about Kalman-Bussy filter. So Kalman-Bussy filter has a gradient, Wasserstein gradient descent interpretation, meaning I can explicitly write down what is this F, okay, not this. What is this F, and in that case, what is the distance that I can explicitly write down? And what those papers essentially do, they manually perform this computation over the the mean, vector, and covariance. We recover the Kalman-Bussy equations. We also did the same thing for Onham filter, and we also got it for the the same interpretation for the Onham filter. What we have not done is for the general case. So what we believe, this is true, but we have not done it, is there is a general interpretation in the sense, if you take the Kushner-Stratinovich stochastic partial differential equation, and it might be possible to view that equation, evolution of the conditional joint PDF, as gradient descent of a functional, okay? But that functional will be stochastic. Okay, so that will be a stochastic gradient descent. Some partial results we have is that we can break the problem in simplified way, in the sense you can think about as a composition of prior computation and posterior computation. So prior will be a deterministic proximal, and then posterior will be a stochastic proximal. That kind of result is, I think, possible. But in general, to show the overall thing seems a little bit challenging. So we have not actually gotten time to approach that, but I think that is a very fascinating direction. I believe this is also tractable for so instead of attacking Kushner-Stratinovich, which is nonlinear, so if somebody attacks the linear version, meaning unnormalized version, the Zakai equation, I think that one is a little more tractable. Meaning in terms of computation, I think that convergence, proving the convergence might be a little easier. Yeah, but it's a fascinating direction, and this is something I would like to work on.
Great, thanks.
Sure. Any other questions? I have one. What I actually have two, but I asked the first one. Is there a benefit or a drawback if we have more terms, like if the function is separable as a summation of n terms, do we get benefit if we let the numbers go large and maybe have some mean field structures appearing, or a couple, because the examples were few terms?
Yeah, examples are, we only did 3 terms. That's a fascinating question. Is there a guiding principle for choosing how to split? Honest answer is I don't know. It seems, at least in this example, we should go to extreme, do 1 + 1 + 1. That is the fastest. In terms of runtime, that seems a good idea. By the way, everything I'm showing, it's a software, so it's a fake distributed computing. So I just everything is implemented software. It's not hardware level distributed. So that is something we would also like to pursue. But I do not know if this is a general trend that if you have multiple terms, should you always do 1 + 1 + 1 splitting, and that is good for computation purpose? I do not know. I suppose people who have some experience in partial differential equation people, they have been doing operator splitting for quite some time. So maybe conversation with them may be helpful. I do not know.
Okay, thanks. So I'll leave other questions. I let other questions to be asked before I ask my second question. So anyone wants to ask questions, please unmute yourself or type in your question in the chat. All right, so I asked the second question while people are thinking of their questions. So I was a bit curious about the term nu that you introduce as a Lagrange coefficient for the measures, right?
Yes.
What is the nature of nu? Is it a function or is it a measure? Because I got the feeling that here it feels more like a function, but in the updates is treated as a measure. It's summed with measures.
In the update, it's treated as a function. You are right. In the update, it's treated just like as a vector. In the discrete case, the mu becomes the primal variable, right? So they just become discrete probability vectors over n by 1, where n is the number of samples or grid points. But these are elements of that high dimensional simplex, those mu primal variables, but the dual variables are basically in Rn. Okay, so they're just functions, and in the vector case, they're just same dimensional vectors.
Because I saw in your work that you take the Legendre transform as well. Right,
no,
so you invoke duality in some sense.
That is a little bit different. Yeah, so there is a so what is happening is this thing, so general structure of the problem algorithm is like this at the bottom of this page, this slide. And now whether how to compute this prox that is appearing in the top line, that really depends on what kind of functions I have got as FIs. Okay, so what is interesting here is that suppose, FI is just pure diffusion, okay, just like a heat equation, right? So in that case, FI does not have an advection or drift, right? But this Lagrange multiplier is causing an artificial drift. Okay, so even if you don't want to, talk about drift, you have to, because you need a situation where this is nu is acting like an advection potential, artificial advection potential. Now, if Fi already has a drift, it is only drift, this can actually be solved analytically. You don't need any financial conjugate or anything. If it is, the drift and diffusion, then you do need, something like, then the evaluation of that prox require, this kind of recursion, which requires this financial conjugate type of idea for derivation. So in other words, that proximal does not have purely analytical expression like this. Okay, so this is little semi-analytical in this second line example, because although this expression is closed form, but it has quantities like this lambda 1i and lambda 2i, which should be obtained by solving some coupled equations. But these coupled equations are basically some kind of, what is this called? Block coordinate ascent recursion that is known to be contractive. So this is guaranteed to be converged. It's a contractive recursion on some cone. So this, you obtain that, and then you run another while loop. You obtain these things, and then you plug them in here in this closed form expression. So in this sense, this is like a semi-analytical. Whereas if drift, there is only also drift here. You don't need to do any recursion or anything. It's just closed form. So it really depends on what kind of functions Fi in a computer I is encountering.
Okay, thanks. Other questions from Abhishek? You can also stop recording if you don't want your question to be asked while recording, but all right, so let's thank Abhishek again.
Thank you so much. Thank you so much for giving this opportunity. Thanks, Peter.
All right, yeah, thank you.
Thanks.